All right, let's get right into it. We're about to go beneath the surface of the machines that literally power our world. We're talking about an invisible landscape, a hidden world where the constant battle against friction is either won or lost. Welcome to the world of surface engineering.
We all have this built-in idea that to reduce friction, you want two surfaces to be as smooth as possible, right? Like perfectly polished glass. But what if I told you that in the world of high-performance engineering, that idea is, well, it's just completely wrong? What if the real secret to efficiency isn't smoothness at all, but a very specific, very precisely engineered roughness?
So on the left, that's what we think we want, a surface that's totally flat, no features at all. But on the right, that's the reality of modern tribology, which is the science of friction. It's a whole world of microscopic grooves and dimples and intricate patterns, and every single one is designed for a specific job. The big takeaway here is that we've stopped chasing smoothness and started designing complexity. So in this explainer, we're going to go on a journey from the world we can see all the way down to the atomic scale. We're going to shatter that smooth illusion, then look at the large-scale form of things, dive into those crazy microtextures, see how nature is inspiring these designs, and then we'll finish up with the atomic layers to give the ultimate protection.
Okay, so let's start with that big idea. For centuries, literally centuries, the main goal in any machine with moving parts, from a car engine to an artificial hip, was to reduce friction and wear. And for the longest time, the obvious answer seemed to be just make everything smoother.
But here's the thing. It turns out friction is a multi-scale problem. A surface that feels perfectly smooth to your finger is actually, under a microscope, this chaotic landscape of peaks and valleys. The real game changer came when engineers realized the goal wasn't to somehow flatten this entire landscape, it was to control it, to actually engineer it.
Our zoom-in starts at the macro level. Before we even dream about microscopic patterns, we have to get the big picture right. This is all about the overall shape and the form of the parts, like the bearing you see here.
It is just amazing how many things can go wrong at this scale. Even the tiniest errors in alignment, or just the overall shape, what engineers call waviness, can cause that critical film of lubricating oil to break down. When that happens, you get something called Asperetti contact. That's just a fancy way of saying the highest peaks on the two surfaces literally crash into each other and start grinding away. To stop that, engineers design features like micro bevels. These are tiny angled edges that basically force a wedge of oil between the surfaces. This is your first line of defense.
All right. Now we zoom in again. This is where things get really clever. We're looking at textures so small you'd need a powerful microscope to even see them. Engineers are literally carving entire landscapes onto metal surfaces.
And there are two main ways to do this. You can either create these tiny bumps that stick out, those are called protruded textures, or you can create these tiny little divots, which are called dimples. Both of them can seriously boost performance, but they work in totally different ways, so picking the right one is absolutely critical. Now check this out. This shows you one of the coolest functions of those dimples. So picture a tiny, nasty particle of metal or grit floating around in your engine oil. On a perfectly smooth surface, that particle gets dragged around, scratching and gouging everything. But with a dimpled surface, that little piece of grit can fall into one of these microscopic pockets. It gets trapped, safely out of the way, protecting the main surfaces from damage. It's like a tiny, brilliant little trap.
The level of detail here is it's incredible. It's not just about having grooves. It is all about the shape of those grooves. An arc shape, for example, might be used to make a bearing stiffer. A rectangular groove, that's great for creating a seal. A V shape is fantastic for reducing wear. And a spiral can create a continuous film of oil. Every single shape has a specific job.
And just to show you how ridiculously precise this science is, research has found that for those V-shaped grooves, the absolute best peak performance for reducing wear is achieved when the angle of that V is exactly 103 degrees. Not 100, not 105, 103. That's the level of mind-blowing detail we're talking about here.
So you have to wonder, where do engineers even get these ideas for such complex patterns? Well, a lot of the time, they look to the best engineer there is, nature. This field is called biomimicry, and it is completely revolutionizing surface design.
Think about it. Nature has been solving friction and flow problems for millions of years. So now, engineers are copying the diamond-shaped patterns from shark skin to improve lubrication. They're replicating the incredible grip of tree frog toes using hexagonal patterns. They're even creating surfaces that mimic a pitcher plant's slick, lubricant-infused walls.
This quote from one of the research papers just says it all. Scientists literally studied the skin on a tree frog's toe, and they found that its hexagonal pattern creates these tiny microchannels that help it stick to soaking wet surfaces. And now, that exact same pattern is being used to control how fluids flow in high-tech mechanical bearings. It's just absolutely fascinating.
Okay, we've gone from the big picture to the microscopic, but now it's time for our final stop, the deepest level yet, the atomic scale. This is where chemistry takes over, creating one last invisible shield against all that wear and tear.
And that shield has a name. It's called a tribofilm. The craziest part is, this isn't something you just apply like a coat of paint. It actually forms itself while the machine is running. The intense heat and pressure from the moving parts trigger a chemical reaction between the metal and the oil, creating a brand new, ultra-thin protective layer right where it's needed most. It's like a self-forming, self-healing armor. And the chemistry of the oil you use, it's everything. Get this. Research shows that a simple methane-based lubricant can form a tribofilm that keeps the metal's original orderly crystal structure intact. But a more complex lubricant, like decane, actually messes it all up. It distorts the surface into a disorganized, jumbled, amorphous layer. It's like turning a neat stack of bricks into a random pile. So two different lubricants create two fundamentally different surfaces at the atomic level.
The possibilities here are just exploding. We're talking about things like diamond-like carbon coatings, using heat to intentionally turn the top layer of a surface into super slippery graphite, or even applying single atom-thick layers of graphene. This is the absolute cutting edge of material science.
So, as we zoom back out, the big takeaway is this. The fight against friction and wear, it's not being fought on some simple, smooth battlefield. It's happening on a complex, multi-layered, brilliantly engineered landscape that stretches from the scale you can see and touch all the way down to the level of individual atoms.
And while every single layer matters, this gives you a pretty good idea of where the biggest improvements are coming from. Yeah, getting the basic shape right is the foundation. That's about 20% of the job. But the real magic, the vast majority of the performance gains, comes from those clever microtextures and those invisible self-forming atomic films.
And that just leaves us with one final, mind-bending thought. We've gone from simply polishing metal to designing its texture, its chemistry, and even its atomic structure. We're getting unbelievably close to controlling matter at its most fundamental level. So the question is no longer just, how do we reduce friction in an engine? The real question is, what entirely new problems will we solve? What new technologies will we create when we can build the perfect surface for any job, one atom at a time?